Imagine a man sitting alone in a dusty room in St. Petersburg back in 1913. He isn't solving some grand cosmological equation or drafting a manifesto. Instead, he's doing something that looks incredibly tedious, almost trivial. He's reading Alexander Pushkin's poem, Eugene Onegin, and meticulously counting the vowels. Every single time he encounters a letter, he notes whether the next letter is a vowel or a consonant. To any onlooker, Andrey Markov, he just looked like a man who had finally succumbed to the boredom of academia, obsessed with a sequence of letters that seemed to have no practical value. At the time, the world of mathematics was just completely obsessed with independence, this idea that a coin flip doesn't care about the flip that came before it. But Markov was captivated by a different kind of reality. He called it a chain, where the future is, in a way, a prisoner of the present. He wanted to prove that even when events are linked, even when one step depends entirely on the one before it, a predictable order still emerges from all that chaos. His peers, they saw it as a mathematical curiosity. Neat trick for linguists or poets, but nothing more. Then the world shifted. Decades later, that same quote-unquote useless logic that he used to track the rhythm of Russian poetry, it became the terrifying blueprint for calculating the critical mass of a nuclear bomb. Scientists realized that the way neutrons split and collide in a weapon of mass destruction followed the exact same dependency Markov found in Pushkin's verses. This is such a jarring contradiction. The same mathematical thread connects the profound beauty of a poem, the cataclysm of a nuclear explosion, and the secret engine behind the Google search you performed this morning. And it raises this haunting question. If the most complex systems in our world, from the internet to the way an AI thinks, are just links in a chain, how much of our reality is actually random and how much is just a predictable sequence we haven't quite learned to read yet?
That is the perfect distillation of the paradox we're diving into today. It is truly profound how one simple mathematical thread, the Markov chain, connects such disparate concepts. You've got profound human creativity on one end, you have cataclysmic power in the middle, and then the mundane engine of modern information processing on the other. This is a story about mathematical principles, finding the pattern of dependency everywhere they look. And our mission in this deep dive is to trace that exact evolution. We need to examine how this deceptively simple concept of dependent probability evolved into the hyperscale generative AI systems we use today, things like large language models. And then we really have to confront the urgent philosophical questions this all raises about predictability, about freedom, and about control in a digital world that, let's be honest, sometimes feels overwhelmingly deterministic.
Okay, let's unpack this chain, starting right at the beginning. We're in 1906 with Markov's original breakthrough. Historically, mathematics, especially probability, it was just dominated by the rule of large numbers. Mm-hmm. And this rule states that if you perform enough trials, say you flip a coin 1,000,000 times, the outcome will stabilize toward the expected probability, like a 50.50 ratio. But the core assumption was always independence. The past doesn't influence the future.
Exactly. And Markov challenged that. He challenged that prevailing obsession with independence. The standard approach was to only look at independent events, like that coin flip. But Markov said, well, what if the events are linked? What if the outcome of the next event is determined only by the state of the current event? He sought to prove that the rule of large numbers still applies, even to events that are dependent on one another.
And he used his linguistic analysis of Russian text, the vowel consonant counting we talked about, to demonstrate this novel idea. So how did that work mechanistically?
It was brilliantly simple. He categorized every single letter in Eugene Onegin into one of two states, vowel or consonant. Then he calculated the probability of the transition between those states.
So the chance of going from a vowel to a consonant, for example.
Precisely. For instance, he found that if the current state was vowel, the probability of the next state being consonant was a fixed, predictable ratio. And critically, this probability didn't change based on the previous 100 letters or even the previous 100 pages. It only cared about the letter immediately preceding it.
So let's translate that back to our coin flip analogy. If landing on heads made the next flip, say 60% likely to be tails, Markov proved the math still stabilizes over time. You might not see 50.50, but you will see a stable 40.60 split.
Yes, because the chain settles into a predictable, fixed long-term average, even with that dependency baked right in.
And this is what leads us to the mechanics of the chain itself. You said it's defined by just two core mathematical components that make it so powerful and efficient.
That's right. First, we have what's called the transition matrix, which is usually just denoted as P.
Okay, so if the states are our current options, like for whether it could be rain, sun, or snow, what does the matrix actually contain?
It's the full table of probabilities for moving from every state to every other state. So if we stick to Markov's original two states, vowel and consonant, the matrix would contain 4 probabilities. The probability of going from vowel to vowel, vowel to consonant, consonant to vowel, and consonant to consonant. It is the set of rules governing the movement through the system. If you know that transition matrix, you know the dependency rules of the system, whether that system is poetry or, particle physics.
Okay, but that makes sense. And the second component?
That's the initial state vector, or S, and that's simply the probabilities of starting in each state. If we apply this to the weather, the initial state vector just tells you the odds of the weather being sunny, cloudy, or rainy right now at the very start of our observation.
So you combine the initial state, S, with the transition probabilities, P.
And you can project the system's state infinitely into the future.
What's so crucial here, and the reason it became so computationally efficient and adaptable for computers later, is this principle of memorylessness. That's a huge concept, but what does it mean in practice?
The memorylessness principle, it's also called the Markov property. It states that the probability of the future state depends only on the present state. It does not depend on the entire history of how you arrived there. And this is what separates it from these, complex dynamical systems that require huge amounts of computational memory to track every single step. For a Markov chain, once you are in state A, the past just doesn't matter. Only the probabilities encoded in the transition matrix for moving out of state A matter for that next step.
So in a simple next word prediction model, if I'm trying to decide what word follows the dog, a simple Markov model only cares about the word dog. It doesn't need to read the fluffy, brown, 3-legged dog ran. It just keys off that last word.
Exactly. And that computational efficiency made it incredibly scalable and adaptable, which allowed this mathematical thread to jump from literary analysis to applications that genuinely changed the course of world history.
Let's transition to the use case that always shocks me the most, calculating the critical mass for a nuclear bomb. I mean, that's such a huge leap from counting Pushkin's vowels.
It is a truly surprising and sobering application. The process of nuclear fission, the splitting of atoms, is a chain of dependent events that is just perfectly modeled by Markov's discovery. When a neutron hits a uranium nucleus, it splits, releasing 2 or more new neutrons. The system state is basically defined by whether that chain reaction is continuing or not.
And those new neutrons are the links in the chain. They either continue the reaction exponentially or they get absorbed by surrounding material and the chain just dies out.
Precisely. The subsequent state is entirely dependent on the present state. Was a new neutron released, and if so, did it immediately hit another nucleus? This sequence is what determines if the fission process is sustained exponentially. And scientists, particularly during the Manhattan Project, they used Markov modeling to determine the required mass of fissile material, the critical mass needed to ensure the probability of an exponential fission chain was virtually guaranteed.
Wow. So it was a direct application of that probability equalization over dependent events, proving the chain would reach that unstable, explosive state required over time.
That's right. To think that the same math that modeled the rhythm of Russian poetry also modeled the physics of mass destruction, it's stunning.
It really is. And then, decades later, the very same principle revolutionized the digital world with the rise of Google.
The Google PageRank algorithm is, well, it's perhaps the most ubiquitous large-scale Markov application in modern life. It completely transformed how we navigate and consume information. The early search engine war was simply fought on keywords, which led to all these irrelevant or low-quality results. Google wanted to incorporate quality and authority into the ranking.
So how do you model the entire chaotic web as a Markov chain? It seems impossibly complex.
They modeled the entire World Wide Web as one giant state space. So each web page was defined as a state, and the hyperlinks between pages were the transitions. The PageRank algorithm then simulated continuous random traffic. Imagine a hypothetical user just randomly clicking links to see where that traffic would eventually stabilize. The pages that received the most continuous, long-term simulated traffic were deemed the highest quality or the most authoritative, and therefore they ranked highest.
That sounds elegant, but the web is so much messier than Pushkin's poetry. You have broken links, sites that go nowhere, groups of sites that only link to each other. Surely a simulated user would just get stuck or reach a dead end.
And that was the major challenge. It was the big hurdle to achieving that stable large numbers state that Markov promised. If the simulated user landed on a site with no outbound links, the chain would die. If they got stuck in a closed loop, the system wouldn't converge globally. To fix this, they introduced a crucial modification that ensures the chain always converges to a stable solution. the random jump probability.
Wait, you're talking about the famous 15% rule.
Exactly. The model assumes that 85% of the time the user proceeds via an available hyperlink, a true Markov transition based on dependency. But 15% of the time, the user will randomly jump to any other web page on the entire internet, regardless of whether a link exists or not. This seemingly minor random factor ensures that every single page is reachable from every other page. This modification prevents the chain from dying or getting stuck, guaranteeing the system would reach a stable long-term ranking state, which is perfectly consistent with Markov's original principle.
So that slight twist, introducing a small element of pure randomness, was the mathematical sleight of hand that essentially created the economic structure of the modern internet. It allowed a system of dependent events to be applied globally and stably.
Okay, so let's take that foundation now and apply it to the incredible complexity of generative AI.
Right. The development of generative AI is a direct continuation of this statistical quest for predictable sequences. But before we explore large language models, or LLMs, we really need to draw a clear distinction between the two major categories of AI. We hear the term AI thrown around constantly. What is the fundamental difference between the predictive systems we were just discussing, like PageRank, and the generative systems that are now writing essays and creating art?
The distinction is vital. Traditional predictive AI is trained to make a classification or a prediction about existing data. It's asking a closed-ended question. Is this X-ray malignant? Will this person default on a loan? It analyzes existing data to output a label or a risk score. It predicts an outcome that is already in some way contained within the training data possibilities.
Okay, so predictive AI analyzes the past to categorize the present or maybe the near future.
Precisely. Generative AI, on the other hand, is trained to create new data, new text, new images, new protein structures that plausibly resemble the original training data. The machinery, at a foundational level, often uses the very same algorithms, but the intent shifts entirely from classification to creation.
And the Markov model, in its simple form, was really the first generative AI for text, wasn't it?
It was the clear linguistic precursor, absolutely. Early forms of text generation used basic Markov models for simple next word prediction tasks. Think of the autocomplete function you might see in an old word processor or an email program. It took the current word, calculated the highest probability for the next word based on its training data, and just offered that up.
But if we tried to write a 5-paragraph story using a simple Markov model, it would devolve into, well, word salad very quickly. Why?
Because of that memorylessness we discussed earlier, simple Markov models were typically what are called n-gram models, meaning they could only look back maybe 1, 2, or perhaps 3 words, a trigram model. So if I start a sentence with, "The large gray ship sailed towards the distant port," and my simple model only remembers the last 2 words, distant port, it might forget that we started talking about a ship. It could then transition to predicting a word that makes no narrative sense in the long run. It failed to generate plausible, coherent, long-form text because it just lacked that broad, sustained context.
So modern large language models, the LLMs, they solve the context problem. But how much of Markov's simple probability engine is still running under the hood?
Fundamentally, they are an evolution of Markov's concept, just scaled up exponentially. LLMs still operate on probabilistic token prediction within sequences. A token is a numerical representation of a chunk of data. It's often a word, part of a word, or even just a punctuation mark. The model is still, at its heart, calculating the likelihood of the next token in a sequence based on the tokens that came immediately before it.
So at its core, it's still about calculating the probability of a transition from one state, the current token, to the next. It's just that the complexity has utterly exploded.
Yes, that explosion in complexity is the key. We moved from these simple models to systems with billions of parameters. When GPT-2 was released, it had 1.7 billion parameters. Its successors scaled that up to 175 billion and beyond. And what are those parameters? They are the weights and biases, the learned dependencies that the model uses to calculate those transitional probabilities. This huge scale, trained on enormous data sets, much of the publicly available internet text, allows the model to learn statistical dependencies that are almost inconceivably subtle.
And that bridges the coherence gap. It learns which sequences are statistically plausible over thousands and thousands of examples, giving it that uncanny ability to predict the next block of text that sounds human.
Exactly.
The scale explains the plausibility, but it doesn't quite explain how they maintain coherence across an entire article or conversation that spans thousands of tokens. How did engineers overcome that memoryless limitation that plagued Markov's original models?
That is the crucial architectural shift. It was the invention of the transformer architecture and its attention mechanisms, which came from Google researchers back in 2017. This innovation is the bridge between statistical prediction and human-like coherence.
Okay, attention. How does this function differently from just looking at the last few words?
Well, think of attention as a highly sophisticated weighting system. When the transformer processes a sentence, it doesn't just look at the adjacent words. It looks at all the words in its defined context window and assigns a relevance score and attention map for each one. So if you are predicting the last word in a long sentence about a political figure, the attention mechanism is what allows the model to recall the name of that figure from the start of the paragraph and ensure the concluding word aligns with that subject, even if dozens of other tokens have intervened.
So it's a profound shift. It captures relationships across much longer text spans.
Right. It allows the model to understand nuance, intent, and these long-range dependencies that simple, strict Markov models could never grasp. It's what gives the LLM the illusion of memory and understanding.
So modern LLMs are using Markov's probability engine for the raw prediction. But this attention layer provides the massive, flexible, weighted memory and context needed for generating truly coherent, long-form language. It sounds like the highest value of generative AI is really in making machines understand us.
Absolutely. The LLM becomes, as one researcher put it, a terrific interface to machines that are human-friendly. Generative AI takes complex, highly contextual human language inputs and converts them into a standardized, unified token format for processing. It allows humans to communicate complicated intent to a machine naturally, rather than you having to learn the machine's programming language.
And what's fascinating is that this probabilistic sequence-based thinking applies way beyond human text. If you can tokenize the data, the same chain logic holds true.
Precisely. If we can convert the data into a standard numerical token format, whether it's pixels in an image, musical notes, or atomic coordinates, the same mathematical principles apply. We're seeing parallel advancements in domains like image generation, systems like generative adversarial networks, or GANs, or more recently, diffusion models. They iteratively refine their output to generate highly realistic data samples. They are still learning the dependencies that make those patterns plausible.
And the applications are moving so rapidly out of the artistic realm and into hard science and engineering.
That's the next logical step in the chain, isn't it? Generative AI is now being used in sophisticated scientific design. Researchers are using LLM-style architectures to design novel protein structures or valid crystal structures. The system is trained on these vast databases of known stable structures, and it learns the dependencies, the bond angles, the spatial arrangement probabilities that make a structure stable and realizable in the real world. So instead of just creating an image, the model is generating a valid scientific hypothesis or even a fabrication plan for a new material. The Markov chain dependency here goes directly from mathematical probability to physical, functional reality. And this is where the mathematics leads us into the deepest philosophical territory. We've established that the Markov chain reveals predictable order independent events, and that modern LLMs can predict not just words, but human behavior and preferences with stunning accuracy. So we now have to confront the central tension. If we are merely a complex set of predictable transitions, how much of our reality is truly free choice versus a predictable sequence we haven't learned to read yet?
The rise of these algorithmic systems introduces what we could call the algorithmic challenge. We used to debate whether fate or biology determine our lives. Now we have this technological layer that claims to know us better than we know ourselves.
And that technological layer introduces the concept of algorithmic determinism. To appreciate this profound tension, we should probably frame it within the classical philosophical debate. Historically, you have classical determinism, which argues that all events, including our actions, are predetermined by antecedent causes. Our lives are just the inevitable outcome of unbroken causal chains, whether they're physical or spiritual.
And then on the opposite side, you have the idea of libertarian free will.
Yes, often summed up by thinkers like Sartre, who emphasize radical freedom and moral responsibility. This view posits that human choice exists outside of preceding causes. We can always choose otherwise.
And the middle ground has always been compatibilism, which tries to reconcile the two.
Correct. Compatibilism suggests that freedom and determinism are compatible. You are free when you act on your internal desires, even if those desires were themselves causally determined by your nature or your nurture. But the digital world complicates this because technology, using these advanced Markov-driven prediction models, doesn't just observe us. It actively influences our choices through feedback loops. The logic of human agency, that process of self-reflection and decision-making, is slowly being replaced by the logic of machine control.
And this transition is economically driven, isn't it? Largely by the rise of what Shoshana Zuboff calls surveillance capitalism.
That is the engine powering this deterministic shift. Surveillance capitalism's goal is not merely to sell you a product. It is to capture what Zuboff calls behavioral surplus. That's all the tiny data points we generate beyond what is necessary for a service. And that surplus is used to produce increasingly accurate predictive models. These systems then subtly shape and alter user behavior to meet corporate profit motives.
Can you give us a concrete example of behavioral surplus being used to shape behavior?
Sure. Think about using a navigation app. The basic service is getting you from point A to point B. But the behavioral surplus is the data on when you hesitated at an intersection, how quickly you accelerated after a stoplight, or which route you choose when you're given two options of equal time. This surplus data refines models that predict your future route choices, allowing the system to nudge you toward commercial interests, a coffee shop, a specific retailer, not through overt advertising, but by subtly prioritizing certain pathways under the guise of efficiency. They're designed to be engaging and profitable, not to promote your autonomy.
And this erosion of ethical norms, the lack of transparency, it stems directly from that opaque system.
Absolutely. The opacity of these algorithms leads to an extreme asymmetrical power distribution. The systems operate in the dark, and people have very little idea how critical decisions, like their credit scores, their insurance premiums, or even criminal justice assessments, are reached. These systems often lack any meaningful appeal, redress, or transparency mechanisms. And this results in what some call the illusion of autonomy. Users believe they are making decisions freely, but they are being preconditioned by algorithmic curation and predictive profiling, subtly reducing the range of available actions under the guise of personal freedom.
This brings us to a really profound idea. The erosion of the algorithmic self. It's not just our purchasing decisions being influenced, it's the very definition of our identity.
The self is becoming fragmented and co-created with technology. When a system like a social media feed or a music recommendation service doesn't just suggest what you might like, but slowly trains what you think you like by consistently reinforcing a certain type of content, that's what we could call outsourcing the self. Nick Seaver's work describes this resulting algorithmic taste, an identity that's determined more by back-end probabilistic systems than by conscious self-reflection or exploration.
And we as users, we start playing along with the machine. We try to guess what it wants.
Exactly. This is the development of what are called data selves. Users adjust their behavior and their content. This is often called building algorithmic folk theories, where we try to figure out what the algorithm wants and then tailor our posts or our searches accordingly. We feed the machine what we think it wants to maximize engagement or visibility. This risks conformity. It limits the diversity of individual identity and stifles the expression of truly novel or unpredictable ideas simply because the Markov chain prefers predictable outputs.
The ultimate ethical compromise here relates back to the ideals of Kantian autonomy, doesn't it?
It really does. For Immanuel Kant, autonomy wasn't just freedom of choice. It was the ability to legislate moral law to oneself through rational self-governance. It requires critical thinking and self-reflection, but in an AI-enabled setting, that personal reasoning is hacked by technological frameworks, default settings, endless engagement loops, behavioral nudges, all maximizing engagement rather than ethical deliberation. The ability to reflect on and pursue universalizable moral principles becomes incredibly difficult when your choices are being pre-engineered by systems maximizing their utility function, not your moral capacity.
I came across a deep dive that illustrated this so perfectly. A researcher detailed his experiment using an advanced predictive AI to manage his daily life, not just his schedule, but his emotional responses, his email replies, even his interactions with his family. And he noticed that the Markov-driven model, refined by the attention mechanisms of modern LLMs, could predict his preferences and even his emotional outbursts with incredible, 99% accuracy.
That narrative just beautifully illustrates the quiet victory of algorithmic determinism. The researcher eventually stopped trying to override the machine's suggestions. He realized that the fusion of his intent and the machine's probability made his life entirely frictionless. And when the prediction is that perfect, why would you resist?
Right. If the chain predicts everything, our moral accountability and capacity for self-reflection just. they atrophy. We're reduced to being data points to be guided rather than agents to be involved. But this frictionlessness comes at the devastating cost of accountability. If the machine suggests the perfect move, and I take it, and then the outcome is negative, where does the blame land?
That is the moral black hole of automation. Responsibility is spread across so many layers. The code itself, the design teams, the corporate liability structure, state agencies, even so-called human-in-the-loop systems, which are meant to maintain human authority, are deceptive. When a human is tasked with authorizing automated outputs, especially in complex environments like medicine or finance, their control can become skin deep.
What do you mean by skin deep?
Decision makers, they get overwhelmed by the machine's complex output, or they simply trust that 99% accuracy score, and they fall into what's called automation bias. They just trust the prediction. This erodes true justice and accountability. If the human is merely signing off on a deterministically generated outcome, they are not exercising genuine agency.
And that concept is magnified in high-stakes environments like military decision-making with lethal autonomous weapon systems or law WS.
Absolutely. Laws are systems capable of identifying and destroying targets without human intervention. If a wrongful death occurs, the moral clarity of responsibility is just lost. Was it the system that generated the sequence? Was it the programmer who set the initial parameters? Was it the commander who deployed the system? The core issue is that the more data systems gather about us and the more accurately they predict our behavior, the less independent we become. Our freedom of choice is not limited by explicit force, but by the invisible hand of data analytics, constantly curating and modulating our behavior. And this profound philosophical tension between the predictability of the chain and our desire for autonomy is playing out in a real-world strategic showdown over the future of technology. On one side, we have philosophies advocating for acceleration, viewing the chain as an engine that must be unleashed to solve human limitations.
I've heard this called AI accelerationism, particularly the effective accelerationism, or each variant. It sounds almost like a cult-like focus on radical technological progress.
It is a deeply Promethean philosophy. The core argument of ESEC is that unreserved technical expansion and acceleration toward a technological singularity, a point where technology self-improves beyond human comprehension, is not only inevitable but fundamentally beneficial. They view technological stagnation, or safetyism as they call it, as a greater danger than uncontrolled advancement.
So in this view, Markov's chain is the mathematical blueprint for technology to feed on itself. It's the formula for self-improvement. They see the deterministic quality of the chain as the very engine that allows technology to move beyond messy, inefficient human input.
Absolutely. The goal is a breakthrough that dwarfs the Industrial Revolution, a new critical mass of intelligence. They believe the probabilistic logic of continuous expansion will naturally lead to a post-scarcity future, and the only mistake we could make would be to slow down the chain for fear of its ultimate destination.
But not everyone agrees that uncontrolled acceleration is the inevitable or even desirable path. There's a strong counter-narrative pushing for technological progress that is equitable, sustainable, and democratically accountable. The idea of public interest AI.
This perspective inverts the accelerationist view completely, arguing that the technological chain must serve human values, not just pure efficiency. A major strategic component of this counter-movement is the push for true digital sovereignty, particularly in regions that are trying to structurally diversify against the few companies that monopolize platform access and computational power.
This takes the fight beyond simply controlling the data and into controlling the infrastructure and the capital that runs the chain. So what does sovereignty mean in a practical, verifiable sense?
It's defined by three structural requirements, particularly in models being developed in Europe. First, you need a purely local legal entity and jurisdiction. This is essential to enforce local laws, like the EU AI Act, and to guarantee protection from extraterritorial legislation, like the US Cloud Act. The Cloud Act compels tech companies under U.S. jurisdiction to provide data access, even if that data is stored overseas. So if the company isn't legally sovereign, the government can't fully control the data or the system.
So location and legal structure matter immensely for enforcing control over the chain.
They are the foundation. Second, you need factual decision-making power through local capital structures. This means completely local ownership, excluding non-local veto rights or blocking minorities. If a foreign entity holds a significant stake, decisions regarding security, deployment, or ethical boundaries can be subtly influenced or blocked, which undermines sovereignty. And third, and perhaps most critically for technical control over the Markov engine itself, is a sovereign software architecture.
Meaning full auditability of the probabilistic models and the data they were trained on.
It requires in-house developed or open-source software with reliable stewardship. This ensures full auditability, the ability to look inside the black box, and it guarantees infrastructure portability. If the entire stack relies on proprietary software controlled by a single monopoly, then even if the physical servers are local, the system is not truly sovereign. It creates vendor lock-in and dependency.
I read about a fascinating, if a bit shadowy, resistance movement in some deep web forums centered around decentralized developers. One coder, nicknamed Loom, described building a sovereign stack using Markov-based frameworks designed to distribute LLM inference across thousands of tiny, untraceable nodes.
That narrative really embodies the tension between centralization and democratization. To figures like Loom, the safetyism and the regulatory concerns espoused by big tech weren't about true ethics. They were a deliberate barrier, a moat designed to keep the power of the computational chain in the hands of the few. The goal of this counter-movement is to adapt the probabilistic frameworks of Markov chains to architect truly decentralized, ownerless technology stacks, effectively circumventing the monopolies and reclaiming the independence of the algorithmic engine.
And that's the challenge for policymakers imposing ethical guardrails on a technology whose core nature, the Markov chain, is about relentless, predictable progression, especially when developers are actively working to decentralize it.
Regulation is scrambling to keep pace. Legal structures like the GDPR and the new EU AI Act are attempts to reintegrate human judgment and safeguard autonomy. The GDPR addresses the data collection component, but the AI Act goes further, mandating meaningful human control and the right to explanation, particularly for high-risk algorithmic systems. It explicitly aims to ensure that human agency is preserved and that the chain does not become a closed loop of control.
But even in governmental use, algorithmic governance risks reproducing structural inequalities, as we see in large-scale state systems.
Absolutely. You can consider India's Aadhaar system, which is the largest biometric identity system in the world, tied to welfare and banking. While proponents argue it increases inclusion and transparency by streamlining services, critics worry about the inevitable algorithmic errors and the lack of recourse. Without specific safeguards designed to overcome structural bias, the deployment of such comprehensive algorithmic governance limits individual agency and risks systemic injustice. It demonstrates that the chain must be governed by principles of social justice, not just technical efficiency or profit maximization.
So how do we get out of this deterministic trap? If the math is so good at predicting our compliance, what are the practical ethical countermeasures we need to reclaim autonomy?
We need practical countermeasures that are rooted in the design process itself. First is value-sensitive design. This means integrating core moral values, like human dignity and fairness, into the architecture from the very start. They have to be baked in, not bolted on as some kind of post hoc audit.
And crucially, demystifying the black box so we know why the chain made the choice it did.
That's explainable AI, or XAI. We must ensure that the decision-making process of algorithms is transparent and understandable to humans. For high-stakes systems, we need to know which probabilities led to the conclusion. Did the system rely heavily on token sequences from biased data? Did it use an irrelevant input? Enhancing trust and collaboration requires demystifying the transitions the chain is making. We also need what you could call dignity-based design. This means consciously restricting personalization and ensuring exposure to diverse views, rather than simply feeding users the most predictable, highest engagement content. It requires treating users as moral agents capable of independent thought, not just data points to be guided.
And finally, empowering the users themselves to question the chain.
Yes, developing critical agency and digital literacy. Both users and developers need to understand, question, and challenge algorithmic decisions. Autonomy in this digitally mediated arena is no longer a purely self-directed phenomenon. It is becoming more and more co-created with technology. We must actively design systems that facilitate reflection and participation, rather than those that only predict our compliance.
This deep dive has traversed a truly vast philosophical territory. We started with Andrey Markov's meticulous counting of dependent letters in St. Petersburg, and we've ended with the question of whether we can truly govern the vast deterministic engines of generative AI. It's amazing how that simple math, the certainty of a dependent probability, became the basis for a system that now fundamentally challenges the uncertainty and freedom of human existence.
The Markov chain is undeniably the engine of efficiency and technological fusion. It promises a future smoothed of inefficiency, where every choice is optimized and every outcome is predicted. But the crucial challenge for us as humans is to protect the one element that resists being reduced to a probability matrix, the unpredictable, illogical, and inefficient part of ourselves. We have to ensure that the chain, which provides so much knowledge and power, does not become the constraint that determines our essence. The responsibility lies not just in regulating the output of the machine, but in actively designing systems that enhance our agency rather than merely predicting our compliance. The true test of our intelligence is whether we can keep the mathematics open-ended.